Hey guys, so today we'll be finishing up the entire astronomy and cosmology chapter, right? So it's the last chapter of the syllabus pretty much, and it's relatively a short chapter. I'll tell you what you have to focus on. You have to focus on the formulas. There are few, not that many, few definitions, I guess, right? And it's more about remembering the information that I throw at you today. Okay, so remember the formulas. You will have to do a very few basic ditto calculations. You have to remember a few definition and remember the information in totality that I say, because there can be a few SAQ questions that are not exactly 2-mark definitions, but they can ask you why things happen. For example, age of the universe, Hubble's law. They can ask you about how we use standard candles for making measurements. All of these things you'll understand today as we proceed with the entire chapter. So under astronomy and cosmology, the first thing that we're going to be focusing on is luminosity and radiant flux or radiant flux intensity, right? So the thing you guys imagine when we talk about astrophysics or astronomy and cosmology is the big blank space that we have in the universe. You think of a bunch of stars, you think of galaxies, right? You think of supernovas. If you guys know what supernovas are, then great. You think of planets and exoplanets. You think of solar systems, which are all very important things to think about. And what we want to find out first through this chapter is basically the measurement of these stellar bodies that exist in the universe. So you want to be able to measure certain quantities of these stellar bodies. So these can be galaxies, these can be planets, these can be stars themselves, and we will be mostly working with stars, to be honest. We will be working with stars in different phases of their life. So for example, going to supernovas, or they are existing as a bright star like that of our own sun. So we're going to derive and understand how do we know, for example, how far they are, and how bright they are. So these are the physical quantities we are going to try and understand. So the first thing you need to note is, well, different stars in the sky, in the galaxy, in the galaxy will have different brightness, and how that happens and why that happens, we're going to start talking about luminosity. Luminosity is an indicator of how bright something is. As the name suggests, you probably have heard of luminosity at some point, and if you've learned about fundamental quantities, you've probably in that chapter in AS, you talk about physical quantities in general, and you must have learned about luminosity over there. If not, that's fine as well, but I remember going through this. But yes, what is luminosity defined as? Luminosity is defined as the total power output of radiation emitted by a given star. What does that mean? So it is basically the sum of power emitted by a single star. And how do you guys define power? Power is simply the total work done per unit time. So essentially, luminosity is nothing but the sum of the entire power from every angle of the stellar body, or practically speaking, a random star. So if you have a star which is obviously emitting some amount of light, some amount of energy, right? It is emitting energy, practically speaking, and a big part of that EM radiation is visible light. It can be a lot of it can be Literally, it is a continuous distribution of what kind of light is emitted, and varies from radio to gamma waves. So there's a lot of radiation happening, and we're going to be focusing on practically the visible light spectra. We do observe other frequencies as well, for example radio frequencies, microwave frequencies, gamma frequencies, x-rays, all of that, but we're going to right now focus on the visible spectra. So visible spectra, if you don't know, it is, I'm pretty sure you guys know, but it is the visible light spectrum, which talks about from red to violet, and amongst these come Röntgenbeam. I just call it Röntgenbeam: red, orange, yellow, green, blue, indigo, violet. These are the colors that we are going to be focusing on. And why are these colors individual colors? By the way, they're individual colors, or we know them as individual colors because red has a certain wavelength, orange has a certain wavelength, yellow has a certain wavelength, so green and blue, indigo, and so on and so forth. All of these colors have a certain wavelength, which is why they are a different color. So their color is a byproduct of them having a different wavelength. So this concept of wavelength that the colors have is very important for us to study this entire chapter, because majority of what astrophysics is, and this is pretty much my field of study, I practically just study astrophysics, not just, but sure, it's my main area of study. And one of the biggest part of this entire field of study is being able to consider the measurements taken from the universe and making some sort of use out of it using the formulas, especially we're going to show today. Sure, there are more advanced ways, there are more advanced observational techniques, and also measurement and calculation techniques, sure, but at the base of everything, all that you study today is going to be very relevant if you ever take up astrophysics module, astronomy, or cosmology modules. So it's a mix of everything that you will study today. So yeah, luminosity at the end of the day is simply power, total power emitted by any stellar object. Practically, we're going to be talking about suns, and suns are going through supernovas. So it's measured in watt, because obviously we are talking about power, so the unit of this is going to be watt. Okay. So don't get confused. I know a lot of you guys will ask me right now that why are we giving a different name for luminosity? Why not just call it power? Because we're talking about, especially in this case, we are practically just talking about the total amount of light emitted by the body, or total amount of power emitted by the body, and we do this study by observing the EM wave emitted by it, and practically speaking the light emitted by it. That's why we just call it luminosity. So we just consider the power emitted by the star from every single angle, every single piece of area of the star. So when we sum that, when we sum the power of this area with this area, white is a bad color choice. So when we sum up the power emitted at this area, then this area, then this area, and then through the entire body, or that is surface of the area, and the area of the sun or area of any spherical object is 4 pi r squared. You guys know that, twice the normal surface area of a circle, 2D circle. So yeah, when we sum up the power through every piece of the area, that becomes luminosity. Okay, that becomes luminosity, total light emitted or power emitted by the body. So hopefully this part is clear, because this is going to be very important as we tread towards the next definitions. So based on this definition that you have of luminosity, we come to the next thing that we talk about, that is radiant flux intensity, and it is very related to what luminosity in essence is. Okay, so what is radiant flux intensity? We denote this variable and express this as F, okay, because flux intensity, right? This flux intensity. So now, radiant flux intensity, what is this? It is the observed amount of intensity, or the radiant power transmitted normally through a surface per unit area of radiation measured on Earth. So what is this? If I had to re-clarify this, basically it is luminosity per unit area. I know I have written a lot over there, but that is important for you to define something very systematically in your paper. That's why I've written it in a very formal structure and may even seem a bit cryptic in nature. But in essence, in an expression, simple expression, it is luminosity by area. So total power emitted, or total light emitted by the stellar object, divided by the area of the stellar object. So area is basically the surface area of the object. So this spherical area of the whatever we are talking about, and we're going to divide luminosity with it, that is total power emitted by that stellar object. So how do you do that? Basically, what it ends up giving us is, let's say I take a small piece of area, 1 meter square, right? The amount of light or power emitted by that 1 meter square of area of the spherical object is the luminosity. Sorry, my bad. Flux intensity. Flux intensity. So that is flux intensity in essence. The amount of light or power emitted per meter square. So however much power is being emitted over here is the flux intensity. Do we get that? Do we get that? Sure. So it is the energy emitted per unit time per unit area. Do we get that? So energy per unit time is power, right? Energy per unit time is power, and power by area, when I say power, I mean the total power. So total power by the area is flux intensity. Okay, I may be using power and luminosity interchangeably, but yeah, when I say power, I probably mean the sum of the entire power of the stellar body, which is luminosity in essence. Right? Clear? At any point, if you have any question, list it down and just let me know. Okay, mail me or something, I don't mind at all. Okay, so now flux, I will try to explain it using the diagram, which is a bit interesting. So the very fascinating part is the proportionality between how the flux intensity changes with respect to how big or how far away we are from the sun. Let's say the sun is at the center over here, right over here, and there's a light emitting stellar object, which is our sun. So let's say the star is right over here at the center, and 1 meter away from the sun, that is distance r, consider this the basic unit. So let's say we are r meters away, and I will have a flux intensity of, let's say, well, F is going to be luminosity by area. What is the area of the sphere? Please tell me. Right, 4 pi r square. Right, 4 pi r square. This is the area of the circular body, and this is your flux intensity formula as well. Okay, that is your flux intensity formula as well. This is your flux intensity formula. Luminosity divided by surface area. Great. Now notice one thing. If I am not just r meters away, but 2 r away. Okay, notice what happens if I'm 2 r away. Let's see what happens. Flux, this is F1, flux 1 at r, and let's say at 2r, what is the flux intensity? It's going to be luminosity divided by 4 pi 2r whole square. Now let's distill this down over here. I'll break the brackets down or open the brackets, and I'll have 4r square. Fair? So let's bring the 4 right in front. So I'll essentially have 1/4, right? Notice the proportionality, guys. This is the initial flux I had, flux intensity I had, and this is the flux intensity after moving 1 meter away from my initial distance. So as I increase the separation twice, so I went from r to r, my flux intensity decreased 4 times. So what is the proportionality? Increase in distance is twice, decrease in flux intensity is 1/4. So it's an inverse square proportionality, and you should be able to understand that solely from the formula. Do you see the formula? It is if flux is proportional to 1 by r square, inverse square law. So if you increase this, this is something that you've come across so many times through so many different chapters, gravitation law, whatnot, electric fields as well. You've learned about the inverse law and how it works. And also, let me show this through the diagram as well. If this is the amount of light we are analyzing at different position, so I'm just talking about this amount of light, right? Whatever amount of light comes out from this, there's a very beautiful word for it, standard, I forgot the 3D angle unit. Let me search up what is 3D angle name, solid angle. So whatever light is coming out from this solid angle, right, from this solid angle, we're just analyzing that amount of light at different distances away. So we're going to be analyzing how much the intensity decreases based on how much area it's covering, right? So let's observe. I'm just trying to draw a bit better, don't mind me. Right, now it looks much better, does it not? Perfect. So now what do you see over here? What do you notice? The same amount of light that is within that solid angle, whatever the solid angle may be. You guys haven't studied solid angle, it's just angled in 3 dimensions. Just believe me what solid angle is. It is angled in 3 dimensions. So whatever light is coming out from here is the same amount of light over here as well. Do we get that? Hopefully you do. Now look, whatever amount of light was coming in at our distance away, it was covering 1 square unit box. The moment you went 2r away, the same amount of light is covering 4 square unit box. Each of these boxes, please note, is the same size as this box. Please just believe me on that. Although the diagram may not look like that, but trust me, it is. So what I'm trying to say is whatever light was coming in over here got distributed between 4 such area as the initial one. Then you again increase it 1 more radial unit and gets spread out between how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 square units. That is area. So what's happening is the same amount of light is coming in and it is being spread over a larger area. And if same amount is coming in and spread over a larger area, obviously the most important thing that's happening is intensity is decreasing. It is less intense. Intensity is decreasing. I don't think I have to repeat that any more times. Intensity is decreasing. Hopefully you guys take that. I'm taking things very slow because I want to see the fundamental over here. This is not a big chapter anyway, so I can take it a bit slow. So essentially intensity is decreasing, and in what proportion? Let's see again. From here to here, if I have increased the area, separation 3 times, so from r I've gone to 3r, how much do you think the intensity will decrease? Let's see. Initially it was covering 1 unit area, now it's 9 unit areas. So what was being applied over 1 unit area will now be applied over 9 unit area. So intensity will be divided 9 times compared to whatever the intensity was here. Do we get that? So our intensity is 9 times less, which follows the proportionality, my friend. So flux intensity at, not FR, 3R is going to be 1 by 9 L divided by 4 pi R square. Even if you don't believe me, I'll do it again. 4 pi 3 R squared. Do it yourself. Now L divided by 9 times 4 pi R square, because 3 square is 9. So 9, I brought it over here. Do you believe me now? Hopefully you do. I've tried to prove it as many different ways as possible. Does it make sense now? Any question, do let me know, no problem. I mean, you may be watching it later as well, so that's fine. Beautiful. So what is one thing we have established? That the intensity follows this proportionality, where the intensity is going to be inversely proportional to the separation. If separation increases, what happens to my dear intensity? Decreases. Separation increases, intensity decreases with respect to the inverse square law. And radiant flux intensity, which is denoted as F, we can write the entire formula as intensity flux, or flux intensity, is equals to total luminosity or total power divided by the area that power covers. So watt per unit area. This is the definition of flux intensity. You may argue, isn't this the same definition as intensity itself? Yes, we just call it flux intensity. Please don't argue with me. I follow the same rule as you guys. So it's just the name. It's watt per unit area. So yeah, it's the same as intensity you have studied in, let's say, AS as well. It's the same logic. Now, where L is the luminosity of the star, there you go. And area is the surface area of the sphere, there you go. And that is at any given distance, of course. At distance r, this is the area. Oops. At distance r, this is the area. At distance 2r, this is the area. I don't want to erase. At distance 3r, this is the area. Hopefully you lot believe me. Now let's go. I've showed this over here. As you move away from the source of the star, your intensity will keep decreasing. This is the formula. Please guys remember this. By the way, it is d, that the symbol that we use for distance. So this d, distance or separation from the star, light emitting object. Okay. Now there's one more logical thing you can ask me. Do we assume the distance from the center of the star, or do we assume the distance from the surface of the star? What is this d? Well, for one thing, the light is emitting from the surface, but the thing is, it does not matter. It really does not matter. The reason I say this is these stellar bodies in size are so small in comparison to how far they are from us, that it has this distance, that's the radius of the stellar object, is of zero substance and importance to us. It is not going to affect our calculation as a whole. It just is not going to. Okay, so it doesn't really matter what the size of the stellar object is, because they're in comparison to how far they are, it just doesn't matter. So it doesn't matter where you consider the center from, and you don't know the radius. You might figure it out. You might be able to figure it out. There are calculations to do for that as well. But honestly speaking, it doesn't matter. And I know police in A-levels I don't think they'll ask you where you consider the separation from the center of the star or from the surface. But yeah, we are obviously considering the light emitting source, which is we technically consider from the center, but we consider all of the light to be coming from this one point, and then we do our calculation as it is. But yeah, it doesn't matter because the radius in comparison to how far the light emitting source is from us is like really large. So the ratio wise, it's so small, so negligible, so it doesn't matter. Nonetheless, what else? Yep, the equation assumes its power is emitted uniformly. That is to say, intensity at every piece of the area of the stellar object is equal. So if it has an X amount of intensity here, it will have the same X amount of intensity here, because we're distributing a total luminosity over a given area. So it's equally distributed per unit area of the stellar object. So it doesn't matter. Okay. And we also assume that the radiation is not lost in between, because we are making this analysis of flux intensity or luminosity based on the light we capture. Practically speaking, obviously a lot of information has been lost, practically speaking, or added based on what you have between the observer and what you're observing. There may be other light emitting source in between, which is adding noise to what you are observing, or adding excess information to what you're trying to observe. So it may be possible that you have added information in whatever you're collecting, right? So, but generally, yeah, it's mostly information that we lose. So I've written it as, we assume that the radiation is not lost in between, because whatever we take, the total amount of light that we receive, right? We receive a certain amount of light from our observatories, from our technical appliances that we have, astronomical observations. There's certain amount of telescope, different types of them, which capture light at different frequencies, all of that shenanigan. So we receive, let's say, X intensity of light, and this X intensity is obviously not the luminosity of the stellar object, not luminosity. Okay, this is a portion or a part of the total luminosity, or in essence it is the radiant flux intensity. I mean, we find it out as in the area of the stellar object we are observing and the light we receive from that area of so if we are over here, right, and we are observing this part, right, and our technical appliance, whatever we have, is capturing light from this area or this area of the stellar object, then we take that amount of light captured divided by whatever area we were observing or got the light from, and we get the radiant flux intensity. It's just I'm adding that information for you guys to have a better perspective, right? So that is how we do the calculation or whatnot. Sure, there are better ways, more sophisticated ways to do things, but yes, fundamentals are always fundamentals. You need to build on the fundamentals to add nuances and specialization to it. But yeah, we assume radiation is not lost, and we assume that there's uniformity in how the luminosity is spread out through the stellar object surface. I've spent half an hour explaining this. Bad job on me, I guess. Okay, wait. So now, standard candles. This is very interesting. This is something we use as well for our calculations. Is this pulsating or not? Okay, do you see what's happening over here? I'm zooming in. Do you see what's happening? So what you see is a pulsating stellar object. It's called a Cepheid variable. I don't know how to pronounce it. I'm pronouncing it as Cepheid variable or something. So what this is it's a pulsating body of light. What that means is it goes through a high and goes through a low. That is to say, it goes to a point where the intensity is less. That is to say, luminosity in both the periods are same. So it decreases to the small size or not. So this is the small area, right? This is the area, one of the area. Do you agree with me? Now see. Oh, my marking goes away. See, that is small. Now it's big again. There's a color change as well. If you observe carefully, as it grows bigger, it becomes a bit more yellow, and that's for a good reason. We are going to discuss that as well. So what you observe essentially is when it's growing bigger in size, the intensity is decreasing, right? Because it's larger area, okay? And since the intensity is decreasing, right, we see the more yellowish or reddish tone. Nonetheless, that is something I'm just adding over here. But the main conversation of a Cepheid variable and why we're talking about this is it is pulsating. It is pulsing. It is going through a periodic motion. What kind of a periodic motion? I don't like that color. It is pulsating. Is going through a periodic motion. Is going through a periodic motion where let's say it starts at max intensity, then goes to after, let's say, a time t, it goes to lowest or least intensity. Essentially what we observe is not the size of the Cepheid variable, sure you can observe that as well, but what we observe is the intensity. Do I have it? Yeah. So what we observe is the intensity. So Cepheid variable essentially is a type of pulsating star. Of course it's a star because it's a light emitting body, and its brightness changes periodically. So its luminosity changes, not luminosity, its intensity changes periodically. So the specific period of the change in brightness will let us estimate its luminosity. Okay. So what lets us understand its luminosity? By the way, what we are doing over here in the standard candle chapter is we're trying to use something called standard candles to find how far unknown stellar objects are. By the way, I always try my best to lead you guys with a question so you guys know what you guys are studying, and you guys don't just, open your mouth and just look at all the information and be like, oh. You guys want to be able to understand what you're studying, right? So I try to lead you guys with a question so you know what answer we're looking for in each of the chapter. That's why I just take my time to establish these questions. So now look, what we're trying to do is we're using standard candles to find how far unknown stellar objects are, or how bright they are, let's say. How bright they are, or how hot they are. There are multiple pieces of information we can figure out. So in definition, what standard candles are, it's a class of stellar objects which has a known luminosity. So standard candles are simply, the standard candles are stellar objects with known luminosity. And this helps us understand the luminosities of things that are far away and how far they are. Because once we match the luminosity, or we take certain bits of information of how far what type of feature unknown stellar object has, and we match it with the standard candle, we get to know how far it is as well. And I'll show that to you. And one of those variable is luminosity itself, and it's the main thing that we look for. Hopefully it makes sense a bit, at least when we do the thought process of how it's really done. You will get a better idea. Okay, so the standard candles is basically a way to find unknown stars luminosity, and also then how far they are. Okay, so yeah, as mentioned over here, since the luminosity is known, the distance can be found out using the flux intensity formula, because flux intensity says luminosity by area, and area is 4 pi r squared, where r is basically the separation, right? So essentially I get to know how far they are by making d the subject. We know the flux intensity because this is the captured light. Luminosity we get to figure out by comparing with standard candles, and d we make the subject, and we find how far they are. Hopefully you understand what the point of what we're doing right now. Again, coming back to Cepheid variables, what is happening over here? It is a type of a pulsating star whose brightness changes periodically. So how much light it is emitting is going to change every per second, but it is going to go through a cycle, that is. But yeah, then based on that period, so going from the low to high to the low again, that is the intensity, we get to find out its period. So the total amount of time of the cycle that it goes through. This period, if matches with this, with the standard candle, then we know the luminosity of this unknown star. Let's say what you have at hand, this is the unknown star, right? This is the unknown star, and we have a standard Cepheid variable So I mean, Cepheid variable is a category of itself. But yeah, we have a Cepheid variable, right? And it has luminosity L1, right? It has luminosity L1, and it is well, as long as we know it has luminosity L1 and time period, let's say T1, we observe this unknown star and the period of its pulse, right? And when we find out the period of the pulse is the exact same as T1, and we note, okay, it is taking 3 days to pulsate. So let's say T1 is 3 days, then we know that this unknown star is the same category as a Cepheid variable. So the luminosity of this unknown star will be L1. That's it. That is it. Right? And we get to find out the flux intensity of this based on our observation from Earth. Right? So we get to see a portion of this star and how bright it is. Right? We get to observe that compared to, this equation. Where is it? Flux intensity is equal to luminosity by area. So we get the flux intensity value, right? Basically take the total amount of light captured from a certain area divided by the area it was coming from, and we get the flux intensity. And this we allow, or we get to use to understand how far the object essentially is. Now, you may argue with me that how at the first place we are, finding this flux intensity itself, because for flux intensity you need luminosity divided by the area, and we don't know the area because we don't know how far away the Cepheid variable is, and that is ultimately what I want to find out. And you're right to question that. And the thing is, in your syllabus things are quite simplified. I can't really tread into what apparent magnitudes are, what apparent magnitudes are, and what kind of a formula we use to integrate apparent magnitude in the formula and then find out the total luminosity, or how far away the stellar object is. So there's a lot to it, but for now what you need to understand is, granted what is in your syllabus is, granted you have a Cepheid variable, right, which is sort of a standard candle, and you know its period, right, that is 3 days, let's say, and you know the Cepheid variable's luminosity, which that is why it is a standard candle, and you have an unknown pulsating object, and you don't know the luminosity, and you don't know how far it is. So you observe the periodicity of the pulsating object. When you see that the period is exactly same as my Cepheid variable, you also know the luminosity of the Cepheid variable, which is L1. Once you know all of these things, what you do is, based on the flux intensity you have observed, that is flux intensity in your observed periodicity, you use that value. Let's say it again, this is not actually how it's done, but of course let's go with the syllabus. You take the flux intensity that you have observed from Earth, equate that to luminosity that you have found out from the Cepheid variable, divide by 4 pi r square. You make r the subject and you know how far the stellar object is. Practically speaking, that is how you do with respect to the syllabus you have. Obviously things will be done a bit more differently. Granted, you actually don't have a lot of information. There are more complicated formulas. If you want to get into that rabbit hole, and if you want to ask me, I'm more than happy to answer any curiosity in this area. But you can also search and see, or look at research papers as to how these observations are made, how we find out how far away stellar objects are. It's very interesting in general. So yeah, perfect. So hopefully I've established what you need to know, or what the thing that in your syllabus also makes sense. It's not that it doesn't make sense, it makes sense. Okay, I'm not saying it doesn't make sense, it makes sense. Fundamentally speaking, it makes sense. It's just that it's a simplified calculation, but nonetheless, hopefully you understand the calculation itself. So when you're going to be doing the calculation, and they're going to be giving you the formulas, they're probably going to give you flux, they're probably going to give you the luminosity, and they'll ask you how far they are, how far the stellar object is. Will you be able to do the calculation? Yes, you should be able to do the calculation. I just showed you the trail of thought. Okay, so as mentioned, the Cepheids have the same time period and will approximately have the same luminosity, and we have a data set of Cepheid variables with different time periods. So based on that, if we see, okay, the time period is 30. Oh my god, what happened? Okay, so let's say if the time period is around 30 days, then the luminosity should be around, what is this deviation, 10 to 30, so 20, so around, I would say 18,000 or 16,000 your luminosity should be. So your luminosity should be around 20,000, whatever the unit is, for your unknown stellar object. So we have found out, based on the periodicity of, my goodness, so based on the periodicity of the unknown stellar object, we found out the luminosity of the unknown stellar object, which is around 20,000 units. Got it? Or 18,000 units. Got it? So we find the luminosity, and we have the apparent, we have the flux intensity. And based on this, we can do an analysis of how far it is. Do we get that? Hopefully it makes sense. Any question, let me know again, no problem. Okay, perfect. So yeah, there is already a dataset which I just discussed. Fair. Exactly. So if there is 3 days, for example, if the periodicity of the unknown Cepheid variable is 3 days, and we know the luminosity of it should be 1000. So great, based on existing dataset, we can make a lot of calculations, right? Or make a lot of assumptions, better word. Alright. So using the time period of the pulse, we get to know the luminosity of an unknown Cepheid. Now we can use the luminosity and its radiant flux intensity, that is the observed intensity on Earth, which can be measured using a device, obviously, and this is used to find ultimately how far away the stellar object is. Alright, so we know ultimately how to find the distance from Earth of an unknown Cepheid variable that we have yet not classified. Now, a similar thing can be done, which is even further away. So practically, these calculations can be done for things which are somewhat close by to us. Now, what to do with things that are, or unknown streams of light that are way too far away, okay, by several magnitudes. What to do in those cases? So let's say an example of a standard candle in these magnitudes of distance away from us is type 1a supernova. So type 1a supernova, in essence, is nothing too complicated. It is an explosion of a white dwarf. White dwarf is a stage of a sun. It is a stage of a sun, if you guys are confused, right? So basically, the sun goes to a stage where it becomes a white dwarf, and after becoming a white dwarf, what happens essentially is, wait a minute, I have to tie my shoes for some odd reason. Give me a moment. So, white dwarfs are basically the old age of suns, and after a point, basically they explode, right? So white dwarfs explode into supernova and releases a ton of energy, way more than a ton of energy, but you get the exaggeration. It's not an exaggeration, it is less of an exaggeration, if that makes sense. So yeah, a lot of energy is released in a supernova, right? And type 1a supernova is simply a class of supernova, right? Yeah, so when it explodes, the feature of this supernova or specific type of supernova is that when it explodes, the luminosity at the peak of the explosion remains the same for all supernova of the same type. Do you see where we are going with this? So the thing we've classified is at peak brightness. So a supernova basically goes through a process of mass collapse. So the mass collapses, the stellar object the star collapses. That is, it goes through what is that term? I forgot. Implosion. So it goes through implosion, right? Collapses and then it explodes. And in this explosion process, a lot of its mass turns into pure energy. Essentially, a form would be light. Okay, and this amount of light that you see, although short-lived, but the peak light luminosity is intense, is really high, which is why even though they are really far away, we can make measurements of the light or of how far away they are, because it's visible, and it's only visible because the sheer intensity of the light is magnanimous, right? It's humongous. Okay, so that is why supernovas are important for us to understand the vastness of the universe itself. It's an important indicator. I won't say it's the only thing, but sure. So we observe the peak intensity of the supernova, and with the same type of supernova for this specific type, that is type 1 supernova, the peak intensity or luminosity is the same. Not intensity, my bad. Luminosity is the same. So yeah, how do we do the calculation or how it really works? When extremely far away, the individual stars such as Cepheid cannot be studied. However, supernova, which is a star exploding, releases a lot of energy, and it turns most of its mass into energy. One form would be light. This explosion is so bright that it can be observed from really far away. That is, even if it is in distant galaxies itself, we can still make an observation. And when you have the peak of the explosion of the same type of supernova, specifically type 1 supernova, they tend to have the same or similar luminosity, making itself a standard candle. What is the definition of a standard candle, my friend? It is a class of stellar objects which have a known luminosity, right? So we know the luminosity of the type 1 supernova, which is why it is valuable and important to us, because we can make judgment of how far other things are of the same category of supernova. That is, if I have an unknown supernova of the same type, then we get to know how far it is, because we know the luminosity and we have the flux intensity, that is the observed luminosity from us, that is planet Earth, and we make the calculation of how far it is based on those three pieces of information. So luminosity we get from the standard candle, flux intensity we get from our observation, and distance we get to calculate from the equation. Okay, right, so that's how the distance is calculated. Now a common question that you can ask me, although no one has ever asked me, is how do you know the type of the supernova itself? So there is a new supernova, let's say one that happened at our university in 2014, observed from UCL observatory. This is where pretty much I love spending my time in. So it was SN 2014J, and you can see this online. Back then, was it called ULO? I don't know, but now it's called UCL Observatory. So what happened was, by accident, our university had discovered the supernova. So it was a very interesting thing, and you have multiple research papers on this, and then obviously other observatories and other astronomers have added their observation on this and information on this. But yeah, it was very interesting. But let's say something such as this has happened, that we all of a sudden, by the supernovas that are really rare to be observed, probably one was in 1972, then 2014, then back in 1628 or something along those lines, 1600s, somewhere along those, so like centuries before. So it's very rare to be observing supernovas, especially close by and to be identifiable. Nonetheless, what I want to say is, let's say such a case happens that we are observing a new supernova and we don't know the type of it, right? There's an unknown supernova. How on earth do you classify the type of the supernova? How do you do that? Because I asked this because you don't know the luminosity of it. It seems that you can classify supernovas based on the luminosity they carry, but you don't know the luminosity of this unknown supernova. So how do you know if this is the same type? For one thing, the assumption that same type of supernovas have the same luminosity is blatant lie and wrong. Although it is written in the syllabus and over here, it is not incorrect. The way they have put it is not incorrect, because they have said with respect to a specific type of supernova, which is type 1a supernova. So that is correct. But a lot of people have this idea that same type of supernova, all of them will have the same peak luminosity, which is not right. Even there is nuance with this type of supernova. They carry a similar luminosity, but when we're talking about with respect to a specific portion or wavelength, we just look at a specific part of it, right? When we're studying the luminosity, and that we can standardize and say, okay, there's a certain value of the luminosity which is going to be same, granted all the nuances have been considered. Then if it has that luminosity, sure, it is going to be a type 1a supernova. But it's obviously it's more nuanced, but still it can only be said one of the only type of supernova is type 1a supernova. And luminosity in general is not how we classify supernovas. It is not the way. How we do it is based on spectral lines. So type 1 is supernova, when we study it or make observation from our, let's say, observatories, it doesn't have hydrogen H2 lines in the spectral lines, which you will see later on in the chapters. So it doesn't have the H2 lines, which is why we get to classify the supernova as a type 1a supernova. So it is basically based on the spectral line from the supernova that we classify the type of supernova, type 1a, or the there's type B's and all that categories. So based on the spectral line, we classify the supernova, not by luminosity, right? So yeah, what have I written over here? So the type 1a supernova is a special case where this type of supernova has similar luminosity at the peak, but for other supernova it does not exactly work. So yeah, that is true, as mentioned. So in essence, how do you classify the type? Spectral lines. Okay, that's how classification really works. So let's say you know the type of supernova, right? And if it's the same type of supernova, let's say we know it's the type 1a supernova, and if it's the same type of supernova, we can attach the same luminosity value. We can say this unknown supernova has luminosity L1. Based on that, and based on the fact that we have a flux intensity value based on observation made from Earth, we're going to plug those values in. So Fs equals to L by area, and we're going to find the area is equals to 4 pi r square. So make R the subject, and we're going to find how far away the supernova is. Great, makes sense to you guys? Hopefully it does. Now we're going to learn about something else. We're going to learn about the use of light years itself. So, concept of light years, right? Light years is a unit of time. So we categorize time in something called light years, and it is basically how long. Sorry. It is a. What am I saying? It is a unit of distance. My bad, guys. My bad. So light year is a unit of distance. Extremely sorry. It is not a unit of time. It is a unit of distance. So light years is basically saying how far light travels in one entire year. So you have heard of these statements. For example, Earth is 1 light year away from, let's say, XYZ exoplanet. I don't know, I have zero clue, I'm just saying. So let's say something is 1 light year away from Earth. That means for light to travel from Earth to that exoplanet, it will take 1 whole year. Or for anything to travel at the speed of 3 into 10 to the power 8 meter per second, will take 1 year to go from Earth to the exoplanet. So that is what 1 light year means, the distance. Okay, so how do you find that out? Do you know this equation, speed is equals to distance by time? Obviously you do. If you don't, nothing to say. So speed is equals to d by t. Speed is 3 into 10 to the power 8. 3 into 10 to the power 8. Distance we want to figure it out, right? And yeah. Why did I write it there? Speed is 3 into 10 to the power 8. Time we're going to find, distance we're going to find out. Time is going to be 1 year. So 365 into 24 hours a day into 60 minutes an hour and 60 seconds each minute. And take this to the other side. Let's multiply both sides with whatever I have written in the denominator. So distance comes out to be 9.46 into 10 to the power 15. It may not seem like a lot, but trust me, it is quite a lot. Just go by my word. So 1 light year essentially is 9.46 into 10 to the power 15 meters. Okay, and that is what 1 light year means. So it's really far away. So let's say if anything happens at a galaxy that is 1 light year away from us, then we will see what has happened there after a year. Why? Because light would take 1 year to travel to us. So if, let's say, today something happens at galaxy Y, which is 1 light year away from us, then after 1 year we will receive the light from the galaxy showing what had happened today. So it is essentially, what it's trying to denote is whatever information we receive today is basically we're looking into the past. So from the galaxy, whenever we receive any piece of information, that is, whenever I say information, I practically mean EM waves. So any sort of EM wave that we receive, it is basically showing us what happened in the past. So yeah, you can look into the past, technically speaking, but think for things which are really far away. So based on that, we conclude that looking at the past is possible. So we can do a lot of calculations, of course, between light year and conversion to meters. So let's say they ask you convert 2 into 10 to the power 25 meters into light years, and 1 light year is 9.46 into 10 to the power 15. Then you divide whatever the value you have, divide by your meter for 1 light year, and then you have however many light years the I don't know, whatever the distance is, whatever is at the distance. If it's a galaxy is 2.1 into 10 to the power 9 light years away from us. So it's a very valuable information. Good. Yeah, so basically if you're seeing anything from a galaxy which is 2.1 into 10 to the power 9 light years away from us, we're looking at something that happened 2.1 in 10 to the power 9 years before today. Okay, does that make sense? Hopefully it does. This is what the cosmic ladder looks like. This is to say how far we can look into the past or vastness of the galaxy. So the cosmic ladder is basically showing the scale of the universe we live in, something that is nearby the Earth within 1 astronomical unit. Most likely this is the distance between us and the sun, right? So that is 1 AU, 1 astronomical unit. And then you go to parsecs, which is again a unit of distance. So when you're talking about distances which are so vast in the universe, we have our own units for classifying them. But yeah, whenever anything is within 1 light hour, we have a lot of radars which allows us to collect information. Something that is about 200 parsecs away, within the limit of it, we use stellar parallax. Stellar parallax is basically, as we rotate, this is not in your syllabus, so as we rotate, we get to see an object at different angles, and based on the angle we look at it at, we make an intersection point, and based on that intersection point, we get to understand how far this intersection point is away from us. So from us. So basically it is a way to find distances. So this entire side that you see is how we find how far away anything is away from us. Okay, so this is not important, by the way, it's just I've added it within the distance of, it's good to know. A few of you know, it's probably good. But yeah, within 1 AU we use radars. Between 200 parsecs we use stellar parallax. Beyond that we have spectroscopic parallax, so the devices to find out collect light from different angles, and again we use parallax to find how far things are. Beyond that we have variable stars, for example Cepheid variables. Beyond that we have something called Fissure, which I don't know about. This one I have zero idea about what it is. I don't remember it. But yeah, after that, between 1 billion parsec, 1 gigaparsec actually, we get to use supernovas. That is use of supernova SN as standard candles, and based on that we make the judgment of how far any unknown supernova is, right? So beyond that we use theoretical information, that is Hubble's law. So based on Hubble's law, or velocity of recession of any observing body or any other piece of information, we can theoretically find out how far, or any piece of information that we want to find out of a body that is extremely far away, or beyond 100 million parsec. Does that make sense? Yeah, makes sense. Yeah, good. So this is a bit of random information, common things to know. It just adds perspective to what you're studying, that is to solidify whatever I've thrown at you till now. So you guys shouldn't go back thinking, what on earth did I even study right now? So you should be able to stitch back whatever I've thrown at you, right? That's the purpose of what I'm doing right now. The next thing we talk about is Wien's displacement law. Till now we have covered a few things. For example, using standard candles, right? We use standard candles to find unknown luminosity and distances they are at, right? So we have collected a few bits of information till now, and we have made some use out of it, that is luminosity and flux intensity to find variables such as distance, right? Now we can include or try and understand even more, or collect even more information about these stars, right? So how do we do that? One of the few things that we are going to learn about is trying to gauge the color intensity emitted by these stars. That is going to give us a very important bit of information about how warm the surface or the stellar object itself is, right? So let's say you have any sort of star really far away from you, and it is emitting a peak intensity. That is, there's red, there is orange, there's yellow, green, blue, indigo, violet. And on a spectrum, on an EM spectrum, all of these have a different wavelength, right? So let's say this is increase in wavelength, actually increase in frequency. So actually increase in wavelength, let's do that. So red would be on this side, violet would be on this side. So when I plot a graph of the light collected from a distant star, let's say I get a graph somewhat around this. You know what this graph shows me? This graph is showing me that somewhere about here, whatever the color this is, so around yellow, I get to see a peak intensity. That is between the visible light that I have collected, right? The visible light that I have collected using my telescope from my observatory, at the yellow wavelength, wherever the wavelength may be, I see a peak intensity. Peak intensity. And this bit of information at which wavelength we see the peak intensity gives us a lot of information about how warm the temperature or the surface temperature of the stellar object is, or the star is. So this is pretty much a short summary of what we are going to be seeing in depth, right? Let me give you a bit of in-depth picture. So understand that there is a relationship between let me change my marker. Understand that there is a relationship between temperature and the color of flame or a burning object. So remember that when you did, I don't know if you did, actually not flame test, but when you see something burning, right, or if you see any sort of material burning, the flame it gives off, flame color, often indicates the temperature. How so? For example, when you have something more towards blue, indigo, violet, that means higher frequency. Do you agree with me on this? Does that not show higher frequency? Yes, of course it does. Blue means lower wavelength and a higher frequency. Lower wavelength and higher frequency. And what do you know about the energy equation? Higher frequency means higher energy. And higher energy means inherently higher temperature. So the color, in essence, does indicate the temperature of the material, the flame, or how, that is how warm the flame is. You guys must know till now that all flame burning would not have the same temperature. Okay, so the color is an indication of how warm something is. Maybe, right? It may be an indication of how warm things are. There are other things. Obviously, there's the chemistry of certain things where the color can indicate other things as well. But in general, when you're collecting light from a distant object, the intensity curve is very important to us. That is, of the visible light spectrum. It gives us very important information about the temperature of the stellar object. How? Let's see. So remember the Roy-Biv spectrum that we have of visible light: red, orange, yellow, green, blue, indigo, and violet. So red has the longest wavelength, as we know, but the lowest frequency. Okay, so it has inherently the lowest energy, E is equals to HF. Whereas on the contrary, we have blue, indigo, and violet, right? And what happens with these colors is they have a shorter wavelength and hence a higher frequency. V is equals to F lambda, if you guys have forgotten. So inherently that means lambda is proportional to inverse of frequency. A higher frequency means a higher wavelength means a lower frequency, or the vice versa, right? So if blue, indigo, and violet have a lower wavelength, that means higher frequency, that means higher energy. We have established that pretty well. Look at the graph. The graph is very interesting. Please pay attention to the graph. On the y-axis, I have intensity. That is, let's qualitatively explain that as how much of the light. Let's say the y-axis measures how much of the light. Okay. The x-axis measures something else. That is, which light / which color. Do you agree with me? Yeah. So the y-axis measures the intensity, or how much of the light we are able to collect, right? And on the x-axis we have which wavelength we are collecting, or which color we are collecting. So on this axis that you have, again, we don't just collect the visible spectra. Obviously we don't. EM spectra is very big, and we collect light from of a range, right? It's not just, let's say, a specific range of EM. It doesn't just have to be visible. It can be infrared, it can be ultraviolet, it can be a lot. Okay. Now, when you have this graph, the thing that you're looking at, do you see multiple lines? To be specific, there are 4 lines. All of these 4 lines indicate a different temperature. Okay, all of these lines indicate a different temperature. So let's say this is star 1, star 2, star 3, and star 4. All of these graphs indicate the intensity versus wavelength graph collected from each of these individual stars. Okay, already black body radiation. Typically we're speaking about stars, but yeah, so let's say you have the star 1 and you're collecting light from it. What you see is there's a peak at around yellow. That is, I receive from star 1, I receive most of my wavelength, most of my light in the yellow frequency. I do receive intensity in other frequencies as well, however, much less. Okay. Now let's say I'm talking about star 2, which is, let's say, star XYZ. I see that most of my intensity comes from the red wavelength. And there are others in other wavelengths as well, for sure, but it's less. So now let's look at the third one. Star 3, however, has the maximum intensity being provided at a wavelength that is in the infrared range. Now compare the star 4, I get max wavelength at a far right infrared range, the higher wavelength. Okay. So what do we realize over here, guys? What do we realize? What we realize is all of these stars have a different temperature. So when you had a higher temperature, 6000 Kelvin, your max intensity wavelength was more towards a shorter wavelength. When the temperature decreased, your max intensity of wavelength decreased. Your max intensity wavelength increased. What decreased is the frequency of the light. Okay. Your wavelength has increased, that is, your max intensity wavelength has increased, but your frequency has decreased. Now, as you move to more towards a lower temperature, 4000 Kelvin, now it is out of the visible spectra, more towards infrared, which is of course a higher wavelength. Is that right? Okay. Now 3000, even higher wavelength. So what is happening is when you plot this dotted line, you see a kind of graph emerging out of this. You know what kind of graph this is? Very similar to y is equals to 1 by x. So what have I plotted? So as my temperature increases, my lambda, max intensity lambda, or the wavelength at which max intensity is observed, decreases. Observe yourself. As you go from 3000 to 4000 Kelvin, your max intensity is coming at a lower wavelength. 4000 to 5000, max intensity comes at a lower wavelength. 5000 to 6000, max intensity comes at a lower wavelength. So it keeps shifting to the left as temperature increases. That is a shorter wavelength. So the relationship that we established over here is as my temperature increases, the max intensity wavelength decreases. That's very important, right? So higher temperature means higher intensity. Okay. Oh, by the way, just to say that whenever you have a higher temperature, the intensity of all wavelength does increase for sure, because there is more energy being emitted. So in each of the wavelength, we have more being emitted, more light being emitted, more infrared being emitted, more ultraviolet being emitted. So hopefully that is all right. Now, the second thing is, as temperature decreases, the peak intensity is more redshifted. This is a more technical way of saying this, that the wavelength becomes more redshifted. That is, the wavelength increases. Okay, does that sound good? We're on page. Very good. So what is black body radiation? Black body is basically a perfect absorber of light or energy. So it, for example, stars, right? Stars act like black bodies since they absorb all of light. Absorbs all light, right? That is at all wavelength, and do not reflect. So this is an important, this last statement, this last phrase, that they do not reflect, is very important for a black body. They need to be able to absorb everything. Okay, that means that they are black bodies because they are absorbing everything. Have you heard of the blackest material? Vanta black or something like that. It is almost black body because it is being able to absorb everything without reflecting anything. Now, black body radiation is the process that a black body goes through. That is when these stars emit the energy as EM wave at a range of wavelength, that is a continuous graph for each temperature. It is called a black body radiation. So these continuous graphs that you see without breaks, without any eccentric behavior, it is a continuous graph that shows black body radiation. Black body radiation basically means that you have a radiation, you have release of energy at every single wavelength. You have a certain intensity of release of energy at every single wavelength. There is no strong dip at any given wavelength. That is because it absorbs and releases energy at every single wavelength, and it is a continuous graph. Okay, makes sense. So yeah, now with regard to that, you do have one wavelength where a maximum intensity of radiation is seen. That is what we call the peak wavelength, or lambda max, the wavelength at which most of the light is seen, or most of the intensity is seen. Now, what does Wien's displacement law really say? What is it talking about? It says that for a black body radiation curve, the wavelength of peak emission intensity, lambda max, so lambda over here indicates the lambda of light which has max intensity. Okay, so for a black body radiation curve, the wavelength of peak emission intensity is inversely proportional to the temperature of the star or object. As temperature increases, lambda max decreases. As lambda max increases, the temperature should decrease. Fair? And is the thermodynamic temperature, that is temperature in Kelvin. Thermodynamic temperature means Kelvin temperature. Okay. So now obviously if you want to remove this proportionality sign, you introduce a constant, and experimentally it has been found out, that is by, with all that data that we have, it has been found out that the best fit is found with this number, 2.9 into 10 to the power minus 3. So this is something you can remember or not remember, probably given to you. Okay, not given to you. 2.9 into 10 to the power minus 3 is not given to you. So I don't think you need to memorize this. In the question should be given when you have to use it. But if you do keep it in your mind, I guess it's going to be helpful. Not given as in it is not given in the formula sheet. When I checked, do check it again. If not given in the formula sheet, it is supposed to be given to you in the question itself. Okay. If not, well, just remember it's a small number. It's not too deep. And then the unit of this number is km. My man, it is not kilometer. It is Kelvin. It is Kelvin meter. Okay. It is not kilometer. Please, don't say that to me. Okay. Don't say it's kilometer, please. It is Kelvin meter. How does that make sense? Of course, lambda wavelength has a unit of meter, so this needs to ultimately cancel out to have unit of meter as well. So this constant has a unit of Kelvin times meter, and temperature has a unit of Kelvin, so Kelvin can be cancelled, so you're left with meter, which is ultimately the unit of lambda, or displacement, not displacement, wavelength. But yeah, you get the point. So there you go. This is something I have a slab. I'm sorry, I'm very sleepy. My bad. But yeah, when you have higher temperature, there's a shorter wavelength at which the peak intensity is seen, and that inherently means it's a warmer surface, it's more hot, and that would also indicate that a lot of white light or blue light is being emitted. White light in general obviously encompasses of all the wavelengths of light, but essentially I would phrase it as more blue light being seen, so it's blue shifted. Then you have a lower temperature, which means larger wavelength at peak. That means it's cooler in nature. That would also mean that it is redshifted, or reddish or yellowish, right? So that would mean overall the temperature of the surface is lower. Perfect. So high temperature, more energy, and that indicates more energy of the photon. If more energy of the photon, frequency of light given off should be higher as well. So wavelength should be lower. Okay. Now based on that information, of course, that you get over here, you can convert that into energy of the photon. Okay, because we can find out the energy conversion over here. So you can talk about the kinetic energy over here. Actually, you don't even need to do that. Simply if you see the temperature over here, and based on that, so
lambda is equals to 2.9 into 10 to the power minus 3 if I'm not wrong. What is the number? Yeah, 10 to the power minus 3. And then divide by temperature. So wavelength, you can find out if you know the temperature. You find the wavelength. Once you know the wavelength, it's an easy task beyond that. You plug it into this. So you plug in wavelength, you know speed of light, h you know, and E you can find out because hc by lambda, that is how much energy each photon will have. So it's an easy task over there, right? I don't know why I was talking about kinetic energy. I mean, I was relating it to, you know, the thermodynamic chapter. Can they relate it? I'm sure it's not nothing. I don't know what kind of question they would pose. I'm trying to think, but sure, if they can, they might just intertwine thermodynamics and this chapter to pose a question for you guys. But I've never seen. But yeah, now this is a very simple calculation. You know the wavelength, and simply you can find the energy of a photon, hc by lambda. This is a question you can take a look at. Okay, very simple question. The next thing that we're going to be talking about is the Stefan-Boltzmann Law. It's basically a more sophisticated law with more variables, with more information to deal with. Okay, so till now we worked with, oh no, what happened? So yeah, till now we worked with, what did we work with? Luminosity. When talking about standard candles and all that, flux intensity. We took a look at Wien's law, Wien's displacement law, whatever it is, and that inherently talked about, you know, temperature, right? And we also had a conversation about the wavelength or frequency of light being emitted. So these are the things that previous topics encompassed. Now we're going to bring in more variables, and we want to even figure out more information about the stellar objects we are analyzing, especially stars. Okay, so we saw that, let me change, yeah, so we saw that the peak wavelength will vary with a different temperature. Okay, now what we want to see now is how the luminosity varies with temperature and radius. So there are two factors that make up luminosity in general. One, radius, and the other is temperature. You vary either, you will have a different luminosity. That's how it is. And let's see how it works. So we have a very sophisticated law over here. It's a complicated statement, but I'll break it down for you, no worries. So the Stefan-Boltzmann law states that the total energy emitted by a black body per unit area per second is proportional to the fourth power of absolute temperature of the body. I threw a lot of words at you. Let me make it simple. So what it's saying is the total energy emitted by a black body. So let's consider that work done W or energy W. Total energy emitted by it. Okay, total energy per unit area. So per unit area of the circle, and not circle, sphere. So basically like one small piece of area. So how much energy emitting out of this one small 1 meter square unit of area. So the total energy emitted by a black body per unit area, so work done by area, total work done by area per second, so time, is proportional to the fourth power of absolute temperature. Beautiful. Now you tell me, what does work done per unit time mean? If you've said power, then great, I'm really proud of you. Why am I writing R? But yeah, that is power. Work done per unit time is indeed power. Okay, now what is power divided by area? What do you guys know? It is intensity or flux intensity, F. So what we ultimately found out is flux intensity is proportional to thermodynamic temperature to the fourth power, or the absolute temperature to the fourth power. Good. This is what we found out, and this is what the Stefan-Boltzmann law talks about or states. Let's take the trail of thought that we have already established over here. Let's see. So this you're cool with, Great. So flux intensity is proportional to the absolute temperature's fourth power. Now, obviously, the previous step of this, as I had written over here, is that luminosity per unit area. By the way, luminosity I had written as power in the derivation right now over here that I was writing. So luminosity is simply the total power emitted by the black body per unit time. Okay, great. So luminosity by area is the flux intensity, and that is proportional to temperature to the fourth power. Now make luminosity the subject, and you have L proportional to T to the 4th power times area. Let's break down area. L is proportional to T to the 4th power times, what is the area of the surface area of a sphere? 4 pi r square. What you have is L is proportional to 4 pi r square T to the power 4. You want to remove this proportionality sign. We include something called the Stefan-Boltzmann constant. Okay, so as the name suggests, they figured it out. They figured the constant out, and it's called Stefan-Boltzmann constant. So L is equals to 4 pi r square, which is the area, times the Stefan-Boltzmann constant, which is 5.67 into 10 to the power minus 8. This should be given to you in the formula sheet, data sheet, times temperature, that is surface temperature of the star, okay, to the 4th power, right? Great. So now what this tells you is if a star is bigger in size with, let's say, a certain temperature x, the luminosity will be greater. And this inherently makes sense. If I have a star which is small, let's say this size, with temperature 2000 Kelvin at the surface, it emits this amount of light. Okay, a certain amount of light. Now this same star, not the same star, but similar type of star with same temperature, a bigger one. But this entire bigger star, entirety of its surface has 2000 Kelvin. So more of its surface inherently will have the same temperature. That means total power emitted will obviously increase. Now, one thing you can argue that the flux intensity may stay the same, but I don't think the flux intensity will stay. Will it? Yeah, it will stay the same. So yeah, flux intensity stays the same if you do divide by area on both sides. So it does get cancelled out. So F becomes just proportional to the temperature. So obviously, your flux intensity stays the same regardless of the size of the black body, that is of the star. Flux intensity stays the same, but luminosity obviously increases because with the exact same temperature, you have a bigger body. So the total amount of power that is being emitted or being released is much higher, right? Because the same temperature with a bigger area, obviously more energy in totality is being released. Okay, good. So luminosity is just greater when you have higher radius or a higher temperature. Great. So how is it useful? Let's say you have Wien's law, and based on that you find the color at which the peak intensity is seen. So we know the wavelength, and based on that we can find the temperature of the star, okay, using the lambda max. Okay, so lambda max is equals to 1 by t. You know the lambda max because you get a graph from the observation that you make. So you get a black body radiation curve. You find the lambda max equated to this formula, and you make temperature the subject, and you find the temperature of the surface temperature of the stellar object. Now after finding the temperature, we can put it into the Stefan-Boltzmann formula to find the stellar radii. Okay, so we can now find out the radius of the star. So this is how we know so much information about distant stellar objects. It's just this simple. I mean, sure, there are way more nuances to it when you work with in real life, but these are the fundamentals. This is what the nuances are built on. You know, any sort of uncertainty that we're looking at, or XYZ, whatever we're doing. But the fundamental thing is just this. This is how we can figure out how things that are so far away from us, how big they are, how much light they're emitting, how much power they have, how much energy they have. So this entire process, to me at least, seems very fascinating, but because this doesn't come out of, you know, a lab experiment, but rather a clever, formulation of an equation that allows us to find out so much more about a distant galaxy, a stellar object, based on few bits of information that we have. So it's amazing. But yeah, we can indeed find the radius of stellar objects based on the temperature being found out. Let's see the formula. So the temperature, you want to find out the radius, and obviously we would need the luminosity for the calculation to be done. So let's say you have a flux intensity. Based on that flux intensity, or your apparent magnitude of light from a distant star, you can make a calculation over here to find the stellar radii. So anyways, when they give you a calculation, what they will do is they will probably give you luminosity, temperature, and Stefan-Boltzmann constant will be given in the data sheet, and you'll just have to find the radius. They may complicate a tad bit. They can add Wien's law over here and say use your Wien's law to find the temperature, and then do the process of finding the stellar radii. Okay, they may also give you proportionalities to say, if I increase this, how would the luminosity change? Or they may ask you, if I change the temperature, will the flux intensity change? Your answer should be yes. And then they can tell you, well, if I'm not changing the temperature but only changing the size of the stellar radii, or size of the star, will the flux intensity change? Your answer should be no, it doesn't. Okay, so those are some conceptual questions that they can pose towards you guys. Now, the next thing we're going to be touching up on is Doppler's effect, and over here we're going to be using absorption and emission spectra to analyze Doppler's effect, or understand what Doppler's effect is. You guys studied in AS Doppler's effect, that is, the change in frequency of sound when you have a recession, or recession velocity of sound that is moving away from you, or the sound source coming towards you. So this change in frequency, call it, or change in wavelength of sound, that happens when the object emitting the sound moves away from you or comes closer to you. That is, to you, the observer. Okay, so same thing happens with light as well. It's at the end of the day wave, and when a source that is emitting the light moves away from us, there's a shift in the wavelength of all the light that it emits. So the red becomes longer, so more red. Blue becomes so it will become probably more green. Yeah, it will become more green. So everything becomes a bit more redshifted if the light emitting source is moving away from us. So let's say, I don't know why I'm not showing it over here. So let's say this is the source, I am the observer, this is the bright star that I have, and it's moving away from me. For some odd reason, by principle of the universe, let's say, it's moving away from me, and the color that I see of the sun would be a bit fake. That is to say, it's simply that, by principle of the universe, the sun just comes off as a bit more red than it should be. That is, it went through a Doppler shift in its wavelength, all of the wavelength. So naturally, whatever color it was emitting all of the wavelength got redshifted. Now let's say by chance this was coming towards me. I hope it never does happen, but the sun is coming towards me. In that case, what happens is everything becomes blue shifted. So essentially, the blue would become more violet, red would become more orange, orange would become more yellow, and so on and so forth. So the wavelength would simply shrink. This is the wavelength, and it's moving towards us. Then the wavelength would shrink as such as that, right? This is the wavelength, and this is what happens when the object is now, or the light emitting source is now closer to us, and the wavelengths get squished together, right? And obviously if it's moving away, then it's the opposite thing. So if it's moving away, it's the opposite thing. It becomes longer, wavelength becomes longer. Great. So now the thing is, we don't know if the star is moving away from us or closer to us. It is simply by the principle of Doppler effect that we can understand if the light emitting source, a stellar object, is moving away or closer to us. So, as mentioned, if something is moving away, more red; if something moving closer, more blue. And based on that, we made the conclusion that are things really moving away from us, or are the galaxy we're looking at, the nebula structure, or anything that we're looking at, really, the star that we're looking at, is it moving away? We can simply notice the Doppler shift to analyze that bit of information. Let's see how we would do it. Let me give you a bit of an example. You have proper full white light coming in to a cool gas. So it's a cold gas which has all of its electrons sitting or moving around well in the valence shell. No reason to be excited. And the light comes in, and what happens is the electrons in each of the atoms would get excited in the next shell, or valence shell, or some will, I don't know, if it's enough energy, then some may even leave. Point is, excitation takes place. So some of the wavelength will now be absorbed. That is to say that the electrons will gain energy. By the way, this is a discrete process. That is, there's a discrete transfer of energy, because there is only certain levels of energy that the energy change can happen between N1 to N2, N1 to N3, N1 to N4, N1 to N5, or let's say N2 to N3, N2 to N4, N2 to N5, and so on and so forth, between any energy level. But what I want to tell you is, between each of these energy level changes, there's only one possible transfer of energy. So if the energy transfer is quantized or discrete, then the frequency needed for those transfer, that is the frequency of light needed of those transfer, will also be discrete or specific. So when light comes in and electrons get excited to the next valence, not valence necessarily, but next shell, next energy level, then some of these lights will be missing. As you see, red is missing, blue is missing, cyan color is missing, blue is missing, purple is missing, magenta is missing. So all of these colors are missing, meaning at all of these frequencies, an equivalent energy was used for the electrons to be excited. And that's the beauty. That's a very interesting thing. And so what you have over here is an absorption spectra. Good. So certain wavelengths of light were absorbed by the H2 gas. By the way, this is hydrogen gas. Exciting the electron by exactly providing the exact del E value corresponding to the energy level difference between two energy levels. So these excited electrons, when they de-excite, they would also release the energy, but in random direction. So when we are collecting the image, let's say there's a star over here, and around it is a bunch of gas. So when light is emitting, the light that we receive, right? The light that we receive will have these missing light or lines. So basically, what we get is a spectra with missing lines. So it's called the absorption spectra, right? This is exactly what I'm talking about. So now we can study these missing wavelengths from the absorption spectra of incoming light of the stars to predict if they're moving away or closer to us, that is the star itself. Okay, so let's say the red, not let's say, but it is true that red has a larger wavelength, and when objects move away from us, the wavelength increases, or there's a red shift. Okay, so the object light emitting object moving away from us, things become more red. Light emitting object moves towards us, and more squished together, higher frequency. So now let's see what it really means in terms of the spectra itself. Okay, so you have the atomic spectra over here. This is unshifted. So if you have white light going through a bunch of H2 gas, okay, so the white light itself, right, it comes in, and this is H2 gas, and any normal scenario, let's say this light emitting object, the torch, is just static over there, and this is the gas, and when the light crosses through the gas and we as an observer see or analyze the spectra or collect the information with our eyes or whatever we're collecting the information with, when we get it, we get this unshifted absorption spectra. Okay, now when things are more red shifted, notice all the lines, there are same number of lines, but simply the lines are more red shifted or more towards the red. Now what happens when the light emitting object or the star is moving away? Things are more blue shifted compared to the main unshifted one. Things are more towards the blue. Make sense? Great. Now, the thing is, at the end of the day, when we look at any of these spectral lines, it is very easy for us to identify which element it is or what kind of gas the light went through, because H2 will have a very specific design of the spectral lines. And even if we do get shifted spectral lines, it does not matter, because the spacing, that is how much they are away from the unshifted line, is equal at every one of these cases. So if in this case it has moved by 1 centimeter, even in this case it will have moved by 1 centimeter, even in this case it will have moved by 1 centimeter. So all of them get displaced by the same amount. So the ratio by which they get displaced in redshift or blueshift is the same. So it is still easily identifiable for us, that is, as to which element it is. So it is not difficult. Even if it is red shifted or blue shifted, that is, it has went through some sort of Doppler effect, does not matter. We can still identify which kind of an element the light went through. So what the atmospheric condition is of any, let's say, a star or a galaxy. Great. Now, what else can we talk about? Right, I do say, well, the shifted wavelength will all be shifted by the same proportion. So it's unanimous by all the missing lines. So it's easy for us to identify what element it is. So we compare that design to other spectral line graphs, and we know which element it is. By the way, it can also be true that when we collect the image, it is not just a spectral line for just hydrogen. The image that we collect, that we get, is a combination of spectra line, absorption spectra of the superposition of H2, helium, and other XYZ gases. So all of those come in on the same graph itself. So what we do is we take, let's say, the hydrogen, we take the helium, and we pose them together or superpose them together. So we put the graphs together on the same plane, on the same graph, and we see, okay, where should the missing lines be? And we see, okay, there are missing lines that correspond to helium, that is in the collected whatever light we have collected, the absorption spectra we have collected. We match that with existing helium spectra, H2 spectra, and we try to see the resemblance. We try to match, and we see, okay, it does have missing lines corresponding to He or helium spectral lines. It also has missing lines corresponding to hydrogen ones. So we say that, okay, it went through an atmosphere which has helium and also hydrogen. So that is how we get to know about the atmosphere of different places. But now, talking about if something is moving away from us or moving towards us, which is probably a very interesting conversation. So now, what you want to talk about is how much of the shift it is, and how do we measure that, right? So that shift, of course, we are going to be comparing with the unshifted absorption spectra. So when we collect the image and it has some sort of red or blue shift, we compare it with the unshifted spectra that we are supposed to get in static condition. So when you're comparing with the unshifted one, this is the kind of formula you do come up with. So we say whatever the delta in lambda is. So let's say for hydrogen H2, I have a missing line at around 900 nanometer. Now in the shifted or Doppler shifted absorption spectra, what I see is the same missing line comes in at a higher wavelength. So 910 nanometer I get. So in the formula I would write delta lambda will be 10 nanometer divided by the original lambda unshifted one, that is 900. This is equal to whatever the shifted frequency is. So if my wavelength has increased, frequency has decreased, right? So I will have my change in frequency, whatever it may be. I calculate it out. So it's a simple calculation. V is equals to f lambda. So you just make f the subject and find it out. Whatever the shifted in frequency is divided by unshifted frequency, and this is also equal to v by c. That is at what velocity my stellar object is leaving or coming towards us. So the relative velocity of what we are analyzing, is it whatever the velocity with which it is moving towards us or going away from us, and c is speed of light. So just to add perspective as to what v is, let me tell you this. Let's say I am the observer, right? This is my eye, and I am moving back, or I'm running back by 10 meters per second, and I have the sun which is moving towards me at 90 meters per second, right? Now what is the relative velocity between the sun and me? Since I am also moving 10 meters per second backward and sun is also moving towards me at 90 meters per second, well, in this case, the del V or the V would be 80 meter per second. Does that make sense? So 90 minus 10, 80. Right? So relative to us, what is the velocity with which the stellar object is moving, away or towards us? Okay, so relative to me, or as in the observer. So you can equate del lambda by lambda to V by C, or del frequency by frequency by V by C, or even del F by lambda is equals to, del F by F is equals to del lambda by lambda. There you go. And you have one last thing to worry about. So that is pretty much what Doppler shift is. You have to be able to use whatever the formula you have over here to, they'll pose you a question: what is the recession velocity of this galaxy which has this shift in wavelength XYZ? So you'll be able to use this formula, very important, to find out the answer. Now, the last thing that you have to cover in your syllabus for the entirety of A2 physics syllabus, and also astronomy and cosmology, sadly, is Hubble's law and Big Bang theory. Big Bang. So, you have heard of, at least in some capacity, how the universe starts from something and some singular point, and the world has been expanding ever since. So what we are going to look into is how we make sense of that, or how do we come to that conclusion, really. So let's see. When we do plot the graph of are the galaxies moving away from us or not, that is, how many of the galaxies are redshifted, or they have a recession velocity. So what we essentially do, and what Hubble did, was it plotted the recession velocity. Okay, so what it did was it plotted a number of velocities on a graph with, obviously, on the y-axis you have the velocity, and the x-axis you have how far the galaxy is away from us. So let's say a star SN, SJ205 is, let's say, 150 megaparsec away from us. What velocity is it moving away from us with? Okay, it just turns out to be that every single thing around us is moving away from us, everything. But when Hubble is doing this calculation, what he found was a very interesting trend, and you see that trend in this line, and the line shows that the further anything is away from us will move away from us with a higher velocity. Very interesting. So the further any galaxy is away from us, or star is away from us, it will move away from us with a higher velocity. So Hubble decided to plot the data of velocity of recession of a galaxy and how far they are. The velocity of recession we found out basically using the Doppler shift formula. So we know the change in lambda, and the source, normal lambda equated to V by C. C I know, and V I find out. And the distance can be found out using the standard candles and the luminosity formula. So all of these are sorted. We get to do both of these. Now when the data was plotted, what he found out is there's a direct proportionality, and with the proportionality basically says that with the increasing distance away from us, the galaxies are moving away faster. So the recession velocity is faster with increasing distance. Okay, V is recession velocity, by the way. So the velocity of recession, if you do remove this proportionality, you have to introduce a constant. So this velocity of recession turns out to be equal to h naught times d, where h naught indicates Hubble's constant. And by the way, this Hubble's constant keeps changing every day. Not every day, but every now and then it keeps getting more accurate and better. So when last checked, the Hubble's constant was around 2.2 into 10 to the power minus 18. So this is just the gradient of this line. Do you see this line? So h naught is basically the gradient of this line. So velocity x distance, so velocity versus distance graph. So yeah, that is what h naught is. That is experimentally found out. And as we add more galaxies, stars that we can sort of calculate and find information about, the Hubble's constant just keeps changing. Now, why do you have so many anomalies that is so far above, so far down, and probably even has a probably doesn't even have a recession velocity, probably is moving towards us? Why do these cases happen? If every galaxy is apparently moving away from us, then why are some moving towards us? What is this difference in law? In physics, laws can't just exist for one thing. It has to exist for everything. So why are there anomalies? For one thing, it is just that there are galaxies which are rotating. So relative to us, the galaxy may be rotating towards us. So let's say if you have an observer, and we can only observe from this angle, and we can't see this angle much. So when we see from this angle, what happens is this galaxy is just moving or spinning towards us. So there is a blue shift. So we get light that is blue shifted, and hence we think that the galaxy is moving towards us. What it rather is doing is simply spiraling, and we see some of its arms moving towards us. So that is all that it really is. And the other reason that can be is the recession speed of galaxies may be affected by the gravity of nearby masses. So for example, black hole. So there may be, let's say if I'm an observer over here, and I'm observing a star, right? Some sort of a star, and it probably is, or obviously is moving away from us. However, the velocity with which it's moving away is, let's say, less. And that is probably because there is a black hole over here, which is not allowing this galaxy, that star, to move away with the ideal recession velocity that should lie on this line somewhere, given the certain distance. So that is why we have anomalies, why we have such a scatter of plot. But we find the best fit to indicate where technically we should be seeing what the recession velocity should be of a given star or galaxy, granted they are x distance away from us. Right? That's good. And the last thing we want to talk about is the age of the universe itself, and probably the most interesting thing to talk about, and we're going to end with that. So the age of the universe, we start thinking of it with a simple notion that, well, everything seems to be moving away from us, all the galaxies and stars and everything. And what we have found out is the recession velocity is proportional to the distance that it is away from us. So what it really means, as things go far away, they start to go further away with greater speed. So if this is source and this is something, let's say the galaxy, then the further it moves away, the rate at which it moves away increases. So in 1 second from here to here, it goes just 2 meters. But as it moves away, it picks up its speed, and in 2 seconds, it moves a further distance. So what it means is, if you're farther away from me, you will have a greater speed. So greater velocity at farther distances. So what that inherently means is everything must have started from one singular point and then started expanding away. Now, is this completely true or no? It lacks some evidence and whatnot, but this is a theory that we have. So yeah, if true, then the universe began from a singular point with infinite density, which is extremely hot singular point, which subsequently began to expand very quickly. And this idea is known as the Big Bang Theory. Okay? So based on all the evidence we have before, we can derive the formula for the age of the universe. Okay? So Redshift, of course, gives us most of the information to believe in the Big Bang Theory, because that tells us about the Hubble's law, that when things are further away from us, it has a higher velocity. So that's where pretty much we get this equation from, or I mean law from. But yeah, let's say we know the speed of light, which we do, and we are, by the way, finding out the age of universe. Okay, so let's say we know the speed of light, right? And it has from eternity stayed the same, 3 into 10 to the power of 8. So c, speed of light, is equals to d by t. Velocity is equals to d by t, of course. And now, considering from when the universe started, light did exist from that point onwards. Assuming that, and let's say this is a singular point, light will have speed c, right, from that specific point. And relative to this specific point, its recession velocity would be also c, right? So basically from this point till now today, light has been traveling with a recession velocity of 3 into 10 to the power of 8 with respect to this point, singular point. So what is the distance that light covered from beginning of universe? C, speed of light or speed of recession, times the time or age of universe. Okay, so what is the distance light covered? It is equals to c times t. That is time from Big Bang till now. All right, now v is equals to h naught d. This is the formula that we know, Hubble's law. And what is v in the light's case? C, speed of light, 3 into 10 to the power 8. H naught is a constant, and d is something that we don't know of. Okay, but we can simply say that the distance can be expressed as speed of light times the time that light has been traveling for, which is the age of the universe. So we just substitute this expression into d, and what we have is c is equals to h naught times c times t, and c gets cancelled, and what you have, very interestingly, is age of universe is equals to 1 by h naught, or the Hubble's constant. Fascinating. So as the h naught gets more accurate, we have a more accurate gauge of the age of universe. Let's do a calculation. We know the Hubble's constant, which is 2.2 into 10 to the power minus 18, and when you do the calculation, you get t is equals to 4.55 into 10 to the power 17, and divide that by days, hours, minutes, and seconds, and what you will ultimately get is in terms of years. So it is 14.4 into 10 to the power 9 years old, or 14.4 billion years old. So there you go. It can be, I don't know, 14.6, I guess, somewhere it's quoted. But anyways, as the Hubble's constant changes, h naught changes, your age of universe also changes. So that's why you see age of universe with different values everywhere. But there you go. It's a very small chapter, the astronomy chapter, Astronomy Cosmology. And we've learned a lot of things. You know the basics of how to handle astronomical observations, what to do with it, what sort of calculation to do, and how the age of universe is determined. You've learned a lot. And it's all very, very interesting. And this is something that till this day, I teach, I learn, I get fascinated by. I love it. This is all I do, pretty much. And I love doing this. So there you go. There you have it. And that marks an end to the A2 Physics live batch. Hopefully I could help in somewhat way to you all, to a lot of you guys. Some of you guys will be watching now, some later, and some online from YouTube. So to all, I just want to say, keep working, keep studying, have fun. It's a lot of interesting thing that you're learning. Practice a lot of people. It's not difficult. Trust me, it's not difficult. It's an easy A star, whatever your metric of success may be in the subject, you can achieve it. Just keep grinding, keep doing it. I know you can do it. Okay? And I've tried my best to put out as much good content as possible from my end. So it's been my pleasure to be helping you guys. Hopefully I have done some amount of good. Hopefully I've helped in somewhat of an amount. Hopefully. And would be happy to see a lot of you guys making great use out of this entire series. So yeah, see you guys. Hopefully, hoping a lot of big success, whatever you guys may be doing in the future. All right, best of luck. That marks an end. So bye bye. See you guys some other day, some other time, for some other reason. Bye bye.